Assalamu alaikum warahmatullahi wabarakatuh. This is a new paper, Physics IGCSE, October November 24, paper 41. Question 1. A spring is suspended from a clamp. Figure 1.1 shows the pointer attached to the lower end of the spring. A student suspended loads of different weight from the spring and records the readings on the meter ruler. Figure 1.2 is the reading weight graph that is the student obtains. Using figure 1.2, determine the reading on the meter ruler when no weight is attaching to the spring. When there is no weight attached to the spring, so the load or the weight should be 0. So see here, add 0. We'll move here at this point. This is 40, 50. So here's 42, 44, 46, 48. So the point here is about 43 and the unit here centimeter. So when no weight attached, the reading is 43 centimeter. When a weight of 5.6 Newton is attached to the spring, 5.6 here, to the point 5.6 here, we'll take a line from 5.6 to the reading. This is 62, 63. The point is between 62 and 64, so it is 63. So the answer here is 63. The answer. Calculate the extension of the spring when the weight attached is 5.6. The extension at 5.6 equals the length at 5.6 minus the original length. 63 minus 43 equals 20 centimeters. So the extension equals 20 centimeters. Using the values found in A, calculate the spring constant. Equals F over X. The force is 5.6 and the extension 20 centimeters. It equals 0.28 and the unit here is Newton per centimeter. So the final answer 0.28 Newton per centimeter. An object of mass 0.5 kg is attached to the spring. Calculate the weight of the object. The weight equals mg, mass times acceleration. The mass is 0.5 and acceleration 9.8 equals 4.9 Newton. Final answer 4.9 Newton. The object is pulled until the tension in the spring is 6.5. The object is released. Calculate the acceleration of the object immediately after it released. The force equals m times a. So we need acceleration a equals f over m. What is the force here? The object, as you see here, under of two forces. First force is the force of the weight and the force of the tension in the spring. So take the resultant force. The resultant force equal the difference between them because they are in opposite direction. So the resultant force Fr equals T, force of tension minus the force of weight. Tension here 6.5, the weight is 4.9 as you calculated equals 1.6. So we write here force 1.6 divided by the mass 0.5 gives you the 3.2, the acceleration 3.2, and the unit of course meter per second square. Final answer 3.2 meter per second square. A drag car is a racing car that is powered by a rocket engine. A drag car accelerates uniformly from rest until it reaches the finishing line. The engine is then switched off and the parachute opens. The car decelerates until it stops. Figure 2.1 shows a drag car decelerating after a race. The car has a mass of 1,400 kg. Figure 2.2 is the speed-time graph of the car during a race on a straight horizontal track. The car reaches its maximum speed 130 at time 6.5. Time here 6.5, it reaches maximum speed 130. Calculate the maximum momentum of the car during the race. Mass times velocity. Maximum momentum is when we have the maximum speed, mv max. Mass of the car is 1,400 and the maximum speed, as we have here, 130 equals 180,000, and the unit is the unit of mass and speed, so kilogram meter per second. So final answer is 1.8. How many zeros? 1, 2, 3, 4, 5 times 10 power 5 kilogram meter per second. State the features that is represented by distance traveled by the car. Where we can find the distance traveled by the car, this is the area under graph. Area under graph. Determine distance traveled by the car in the first 6.5. In the first 6.5 we have this area, a triangle. So distance traveled is this triangle. Okay. So distance equal area of the triangle. Distance equals the area of triangle equals half times the base 6.5 times the height 130. Half times the height 130. The base 6.5 equals 420 meters. The parachute opens at 6.5 and the car decelerates. Describe how figure 2.2 shows that after 6.5 the car decelerates. As you see here, how the car decelerates, we have the curve is going down, means the speed decreases. The gradient of the line is negative. The deceleration of the car is not constant. How we know that the deceleration is not constant? We don't have a straight line. This is a curve, which means it is not a constant deceleration. Or the gradient of the line is not constant. Describe the energy transfer that place as the car slows down. Kinetic energy of the car transfers into thermal energy. Question 3. Define the moment of force and describe the effect that it measures. Moment of force is the product of the force and the perpendicular distance from the pivot. And the moment is measures the turning effect of the force. A large rectangular block of stone has a square base of side 4.3. Figure 3.1 shows the block at rest on a horizontal surface. The block is of uniform density and center of gravity G is at its center. Explain what's meant by center of gravity. Center of gravity is a point inside the object where the whole weight seems to act. This is the definition of the center of gravity. The weight of the block is 1.3 times 10 power 7 Newton. Calculate the moment of the weight of the block about the corner x. At the corner x, the force affecting is the force of the weight, which starts the force field from the center of gravity. And the distance between the perpendicular distance between the force and the corner x is this distance, is half of the thickness of the cylinder. So the distance equals 3.4 divided by 2 equals 1.7. Moment equals the force times distance. The force is the weight, which equal 1.3 times 10 power 7 times the distance, as we calculate 1.7. So the moment equals 2.2 times 10 power 7, and the unit of force and unit of distance, Newton meter. Final answer 2.2 times 10 power 7 Newton meter. The block shown in figure 3.1 is in equilibrium. State two different conditions that apply when the object in equilibrium. Object in equilibrium when there is no force or moment acting on it. Zero resultant force and zero resultant moment. Question 4. Describe an experiment to determine the specific heat capacity of aluminum. You may draw a diagram. Include in your answer the measurements made, any equations needed. Okay, first we'll draw the diagram. In the diagram we have here a metal block with two holes inside it, thermometer and emerging heater. Tools: a uniform aluminum block with two holes inside it. We need also thermometer, power supply, immersion heater with known power, and stopwatch. Procedures: measure the mass of the aluminum block M by the balance scale. Put the thermometer in the first hole of the aluminum block and put the heater in the second hole. Measure the initial temperature of the block, theta I. Connect the heater with the power supply and start the stopwatch. After a certain time t, switch off the power supply and record the final temperature theta f. Calculate the thermal energy supplied to the aluminum block E from the equation. E thermal energy equals the power P times time T. Calculate specific heat capacity of aluminum C from the equation. C specific heat capacity equals E thermal energy divided by mass M times change temperature theta F final temperature minus initial temperature. This is how to calculate specific heat capacity. An aluminum dish initially at room temperature, boiling water is poured into the aluminum dish, as shown in figure 4.1. Explain why after a short time the dish and the water are in the same temperature. Thermal energy transfer from the higher temperature, which is the boiling water, to the lower temperature, which is the aluminum dish, until they reach thermal equilibrium and become at the same temperature. Explain in terms of particles why aluminum expands as the boiling water is poured into the dish. As the boiling water is poured into the dish, the temperature of the dish increases, the kinetic energy of the particles increases, the distance between the molecules increases, the volume increases, and the dish expands. The water in the dish evaporates. Explain in terms of the water molecules what's meant by evaporation. The escape of the most energetic particles on the surface of the liquid. Question 5. A loudspeaker produces a sound wave in air. The distance between the center of the compression and the center of neighboring refraction is 0.1 meter. Calculate the wavelength of the sound wave. If we check here, this is the sound waves. He said here the distance between the center of compression and center of neighboring refraction. This center from this compression and the refraction. This distance is 0.1. What is the wavelength? The wavelength is the distance from center of compression to the next compression. So this distance consider a half wavelength. So the wavelength should be 0. So wavelength equals 2 times 0.1, which equals 0.2 meter. Final answer 0.2 meter. State the typical value of speed of sound in air. This is a number to memorize. It's about 340 meter per second. Calculate the frequency of the sound waves from the loudspeaker. You write the equation of the speed of the wave, which is V equals lambda f. So the frequency F equals V speed over lambda, V 340 divided by lambda 0.2 equals 1700 hertz, or we can write it as 1.7 kilohertz. Explain whether the sound from the loudspeaker is audible to the human with normal hearing. The human ear can hear between 20 Hz and 20 kHz, and this sound 1.7 kHz is in this range. So the sound is audible for human ear. Why? Because the frequency more than 20 and less than 20 kHz. Another loudspeaker produces sound of waves 0.4. Sound from the loudspeaker reaches sound absorbing surface with a gap of y is 0.8 at the center. Figure 5.1 shows the arrangement. Explain whether it's possible to detect sound from the loudspeaker at either point J or point K. In point J, this is beside the gap, and point K in front of the gap. First, the diffraction here will be less. Maximum diffraction can be obtained when the wavelength equals the width of the gap. So we'll have maximum diffraction like this. But here the width is much more than the wavelength, so we'll have less diffraction. It looks like this. So sound cannot be here at point J, but in point K in front of the gap we can hear it. So we can say at point G the sound is weak, because at the width of the gap is more than the wavelength, the diffraction is little, so less waves reaches point G. About point K, normal sound can be heard in front of the gap. So normal sound is heard as point K is in front of the gap. The next question 6. A potential divider is made by connecting a light depending resistor LDR and thermistor in series. Figure 6.1 shows the potential divider, the voltmeter, and direct current DC power supply connected into the circuit. The voltmeter measures the potential difference across the LDR. Define the potential difference. Potential difference is the work done to transfer a unit charge between 2 points. The electromotive force EMF of the power supply is E. Describe how the potential difference across the thermistor can be determined using the reading on the voltmeter. As you see here, the thermistor and LDR are connected in series, so the power supply or EMF here divided between them. So we can write this equation E equal V of LDR, potential difference of LDR, plus the potential difference of thermistor. So if we know from the voltmeter here the potential difference here and the EMF, so can find the potential difference in thermistor equals E minus V LDR. The potential difference across the thermistor is the difference between the EMF and the reading on the voltmeter. The resistance of the LDR decreases and the resistance of the thermistor increases. State what happened to the light intensity incident on the LDR and the temperature of the thermistor. Intensity of light on LDR. LDR decreases, so then this light increases inversely proportional. The temperature of thermistor. Temperature of thermistor increases, so the temperature decreases, also inversely proportional. Explain what happened to the reading on the voltmeter. What happened here? First, we know that the EMF is constant, so V of LDR and V of thermistor is also always constant. Right, what happened here? The resistance of the thermistor increases and resistance of the LDR decreases. So the potential difference is directly proportional to the resistance. So the potential difference of thermistor increases and the potential difference of LDR decreases. The voltmeter on the LDR, so the reading on the voltmeter is also decreased. A solid bar is inside a copper solenoid. Figure 7.1 shows the copper solenoid is connected in series with the battery and variable resistor. The device shown in figure 7.1 is an electromagnet, suggests suitable material for the bar. Suitable material for the bar, of course, will be soft metal, like soft iron. The right hand of the bar is S-pole. Figure 7.1 shows the bar viewed from the above. On figure 7.2, draw at least 6 field lines to show the pattern and direction of magnetic field surrounding. This is south pole, so this should be north pole. And magnetic field lines getting out from north to south, so it looks like this. The resistance of the variable resistor increases. Explain what happened to the magnetic field surrounding the bar and state how the pattern of the field lines that represent the field changes. The resistance increases, so the current decreases. Magnetic field strength also decreases. The separation of the magnetic field line distance between lines increases. A square coil of many turns is placed close to the bar. Figure 7.3 shows the plane of the square coil parallel to the flat circular surface at the right hand end of the bar. The resistance of the variable resistor is alternately increased and decreased. Explain what happened to the wires of the square coil. As the resistance changes, the current also changes and the magnetic field strength changes. which induces a current in the square coil. A nuclear mutation of the radioactive isotope of carbon-14, C6N14. Using the symbols shown in figure 8.1, draw a diagram to show the number of electrons, neutrons, and protons in the neutral atom of carbon-14 and how they arrangement. Let's start first with drawing the nucleus. There is protons and neutrons. Protons, as you see the symbol here, a black circle. So write how many protons. We have 6 protons. So we'll draw 6 protons. Then we'll draw neutrons. How many neutrons? Here, 14 minus 6, 8. We draw a symbol white circle. 8 white circles. 1, 2, 3, 4, 5, 6, 7, 8 white circles. Now we'll draw the electrons. This is the neutral atom, so the number of electrons is the same as protons. We have 6 protons, so we'll have 6 electrons. 6 will be divided between 2 inner shells. The first one, there is 2 electrons here. Then the second one, 4 electrons. And the second, so the sum of them is 6 as the protons. Describe how the composition of neutral atom of carbon-14 is different from the composition of neutral atom of nitrogen. They are different elements, nitrogen and carbon, so they have different number of protons. Number of the atom of carbon contains 6 protons, but the atom of nitrogen contains 7 protons. Or the atom of carbon contains 8 neutrons, and the atom of nitrogen 7 neutrons. Carbon-14 decays by beta emission. State the name of the particle that is identical to beta. Beta negative is identical to an electron. Describe the change that takes place in carbon-14 as beta particle is emitted. One neutron changes to proton, or the proton number increases by 1. The half-life of carbon-14 is 5,700 years. A very old object is made of wood. It contains 1.2 times 10 power 11 atoms of carbon-14. When it was manufactured, it contains 9.6 times 10 power 11 atoms of carbon-14. Determine the time that has passed since it was manufactured. Okay, the initial number is 9.6 times 10 power 11. After one half-life, the number decreases to its half, so it becomes 4.8 times 10 power 11. After another half-life, decreases to half, 2.4. After another half-life, decreases to half, 1.2. So this is the final number of atoms, 1.2 times 10 power 11. So it means that there are 3 half-lives. 3 half-lives, each one is 5,700. So it equals 17,000 years. The age of this food is about 17,000 years. The Milky Way in the galaxy is in which the solar system is located. State what a galaxy is. A collection of billions of stars which are gathering to each other by the force of attraction. The Milky Way has a diameter that is approximately equal to 100,000 light years. Determine the distance in kilometers. Okay, 100,000 times 3 times 10 power 8. This is in 1 second. We need to reach 1 year. So times 365 times 24 days times 60 times 60 gives you about 9.5 times 10 power 20 meters. But we need this number in kilometers, so we'll decrease the power here by 3. So it becomes 9.5 times 10 power 17 kilometers. Astronomers determine the speed of distance from the Earth of a far galaxy that is moving away from the Earth. State one observation that allows the speed at which a galaxy is moving away to be determined. One observation can have two. One of them is redshift. Redshift is the increase in the wavelength of the light of the galaxy. State one different observation that is used to determine the distance to a far galaxy and light intensity of the galaxy and supernova. State how the speeds of the galaxy and their distance from the Earth are related. Speed and the distance are directly proportional, V proportional with T. The best estimate for the Hubble constant HO is 2.2 times 10 power negative 18 per second. Use the value to calculate an estimate for the age of the universe. The age of the universe is the inverse of the Hubble constant. So we can say the time equal 1 over Hubble constant, which equals 1 over 2.2 times 10 power negative 18, gives you about 4.5 times 10 power 17. This is an estimation for the age of the universe. Thank you. Goodbye.